So today we'll talk about understanding and visualizing convolutional neural networks. This is one of my favorite lectures to give because we'll get to look at a lot of pictures, videos, have a lot of fun, and there's a lot of space for kind of intuitive understanding of what ComNets are doing. Before we dive into it, just some of the administrative items. Assignment 1 is now graded. We'll send out the grades tonight. I'm saying or so because just in case that something goes wrong and we can't find a way to send it out to you, but definitely we'll try to have it out by tonight. Assignment 2, just a reminder, is due this Friday. You have to submit it differently from last time. So last time you submitted on the Dropbox in coursework. This time please submit in an assignment tab. That's a difference from last assignment. So for assignment 2, submit it in the assignments tab. And as a reminder, midterm is next week on Wednesday. And so I posted some information on the Piazza about the midterm and the sample midterm as well. Oh, and some small fun piece of news is that ResNets, the winning models from 2015, the large 152-layer model is now has now been uploaded. The weights have been uploaded to GitHub, and so you can use these models now in your projects if you like. So this is a Caffe model, but I think several other packages should be able to load it as well. But we're not 100% sure about it, so you have to check it out. But yeah. So we're talking about convolutional networks. We saw that ComNets are useful in a wide variety of application domains. In 2 lectures ago, we saw how convolutional networks work. So we have these conv, pool, fully connected layers. We're stacking them up into architectures. We looked at all the winning architectures over the last few years, and you got a sense of how we actually wire up ComNets to get award-winning performance. And then a lecture ago, Justin was talking about object detection localization. So in this case, we looked at RCNN, fast RCNN, faster RCNN, YOLO, and really how you have this idea of multiple heads on top of a ComNet. So some heads are doing classification, some heads are doing regression, and they're trying to just localize all these things in images in various ways. And we looked into that. So this lecture is mostly about understanding and visualizing. So we'll look at various ways in which we can visualize how ComNets work. So you run a ComNet on ImageNet and you see that your performance is, say, 5% top 5 error, and you can tell that it's working very, very well. But exactly how does this performance come about, and how can we study it or understand what's happening? So we'll go through several of these. I think we'll spend most of the time on the very last one. So I'll kind of like breeze through some of them, some of the earlier ones. So probably the simplest way to actually understand what ComNets might be doing is to look at the raw activations of a ComNet. So in a convolutional network, we pass in the image at the bottom. We get all of these different activation volumes in between. And at the end, we have a classifier on the top. So one of the ways you can study what these ComNets are doing, for example, is we can pick on an arbitrary neuron, say in a pool 5 layer, and we can pipe lots of images through ComNet and just see what excites that neuron the most. So then you get visualizations like this, where, for example, every row here corresponds to a neuron, and every single image here is something that excites that neuron a lot, based on the entire training set of ImageNet. And so you can see that some neurons, basically, they like spotlights, either on the person's forehead or just in general. Some neurons are more interpretable than others. So some of them like text, and some of them like dogs or American flags. So it's not clear exactly what's going on. So not all of them as interpretable as others, but it kind of tells you something a bit. Another way we can study this is not just looking at the activations, but looking at the weights. And in particular, we saw that we can look at the first convolutional layer in the ComNet. And this first convolutional layer consists of a filter bank of filters that we slide over the image. And so we can visualize the raw filter weights. And we can see that the ComNet on the very first layer is looking at all of these different rotated Gabor-like features, as we like to call them. Now, the problem with this visualization, of course, is that this only makes sense to do on the very first layer, where you actually have contact with the raw image. But for the other convolutional layers, they're looking at the convolutional layers below, and so their weights are not very interpretable. So you can still do it. So for example, in my ComNet.js demo, I still visualize the weights of higher convolutional layers. So in the first layer, you can see conv1 filters, and they make sense. The second one is a conv2 filter bank, and every single array in brackets corresponds to a single kind of filter or kernel. And you can see that there's some structure to them, but it doesn't make too much sense. It's not very easily interpretable because these act over activations on the previous conv volume, not on the raw image. So this doesn't make as much sense, and it's not as nice to look at. Now, you might think that, for example, the fact that this emerged just from training is amazing, that you can get these Gabor-like filters out of these networks. It turns out that it's not actually true. In the sense that there were many papers that were written before ComNets where there's many different unsupervised and supervised objectives you can come up with, and pretty much anything you throw at an image where you're trying to learn a feature, with different algorithms, you almost always achieve these Gabor-like filters. So it's not super exciting. There's a bit of a fatigue about it, but basically, I just wanted to point that out as kind of like a fun aside. In fact, the converse is true. It's hard to come up with a reasonable algorithm that does not give you Gabor filters on the first layer. I think the only example I'm familiar with, for example, is PCA. It doesn't give you Gabors, it gives you these kind of wave sinusoids and so on. But anyways. So another way to study ComNets is in this more global representation kind of view. So we looked at filters, we looked at the weights. Another way to study this is we can take a lot of images through a ComNet, and we can look at what I refer to as FC7 features or codes or something like that. And there's 4,096 numbers just before the classifier, right? And so we can interpret those 4,096 numbers as summarizing the content of the image. And so we can think of these as codes. And so lots of images, as we put them through, we get 4,096 numbers for each one of them. And we have a large collection in this 4,096 dimensional space. And now one way to visualize this is, for example, using something called t-SNE visualization. I won't go into details how this works, but it's something that every one of you should be familiar with, aware of, that should be in your toolkit. It makes very nice pictures. Intuitively, what t-SNE does is you give it a collection of high-dimensional vectors, and it finds an embedding in 2 dimensions, such that points that are nearby in the original space are nearby in the embedding. And it does that in a particularly clever way that actually gives you very nice-looking pictures. So here, for example, is the MNIST dataset of digits, which are 28 by 28 images. So this is, I think, 768 dimensional vectors. And they're embedded in 2D, and you can see that the digits from 0 to 9, they kind of cluster in this visualization. So we can run t-SNE on codes of images in ImageNet. And when you do that, you end up with some nice visualizations. So what I've done here is I take all the codes and I embed them. And whatever is close in this visualization is basically close in the mind of the network. You can sort of look at it that way. So there's lots of embeddings here on this website. I preloaded some of it. So this is in the raw space. And then these are some visualizations where I've actually like warped out the representation to make it a square. And then here's actually if we try to zoom in. So these are all, anything that's nearby is basically very similar looking to the ComNet. And so you can see all the headlights kind of cluster here, keyboards, all the circular things. Then we go down, all the spaghetti, mushrooms. There's a cluster on the right here. That's all the dogs are, all the animals in general. Some people cluster in the middle here. Boats, I don't know. So random things, basically. They cluster in a very interesting way. And so that gives you an idea about what ComNet considers to be similar to each other. So you can go through these. They're fun to look at. So that's t-SNE.
How about different types of objects? How are they, why are they close to each other?
Why are they close to each other? I guess it's a very good question. So a ComNet has to classify all these different 1,000 categories, right? And it only has a finite capacity to do that. And so it ends up, in its process of trying to find the best ways to fit the data, it just ends up transforming your images into some kind of a nice dimensional space where it's easy to classify them. And this is a visualization of that space. So I can't say much more than that, basically. So that's t-SNE visualizations, fun to look at. Another kind of fun experiment, kind of on the side, that you might want to maybe perform in your projects, maybe, I'm not sure, is occlusion experiments, which are kind of fun and give you some idea about what ComNets might be doing. What we'll do here is we'll take an image, like the one on the top there, and the ComNet classifies it as a Pomeranian. It's a specific type of dog. And now what we'll do is we'll have a patch of zeros that we're going to slide through the image and occlude part of the image. So there's an occluder here in gray. It's kind of difficult to see. This occluder patch, and we'll slide it spatially through the image. And as we do that, we are looking at the probability of Pomeranian and how it varies as a function of the spatial location of that occluder. And so we're going to carve out and activate a kind of a heat map here of what happens to the probability of Pomeranian as you slide this through. And so what might you expect, for example, from this kind of visualization? What would be a nice result? Yeah, go ahead.
When you cover up the face of the
yeah, so when you cover up the face of this dog, you'd like maybe the probability to go down. So that's in fact basically what happens. And so what you see is the ComNet doesn't care if you occlude any of these regions, but when you occlude the face of this dog, suddenly the probability of Pomeranian plummets. And so that gives you some confidence that basically this is the features that really matter in the prediction. And it's actually looking at the dog. If you do the same here for a car wheel, then car wheel is the region where your probability plummets. For this Afghan hound, if you occlude the dog, then you go down to, the probability goes down by a lot. Interestingly, in this picture, by the way, if you occlude the person's head, then basically the probability actually goes up. So it's kind of like the confidant is not really sure if there's a class here, like maybe there's some class related to a hat on a person or something like that. But once you occlude that region, the confidant becomes more certain that actually Afghan hound is the class for this image. So that's kind of interesting. Okay, so that's kind of on the side, a few things that I kind of marched through as bullet points. We're now going to go into 2 more types of visualizations, and I'll actually show you this video. I'll actually play the 4-minute video in a second. Throughout this video, because it's a very good video by Jason Yosinski, and he has this toolbox called DeepVis Toolbox, and you can download this code and you can run it. And what it's doing, as you'll see, is it's running ComNet in real time, and you can sub in your camera feed and you can play with the ComNet and see all the activations. And throughout the visualization, he'll be showing 2 separate kinds of visualizations for neurons. One is deconv, and the other is optimization based. And we'll cover those later in the class. But for now, I guess these kinds of pictures, you'll see them. We'll cover them in a bit. Let's look at the video. It's a fun video. Oh, shoot. I didn't fully think this through. How do I get lots of volume here? I'm not actually even sure if... Okay, we have to be very quiet, basically.
Recent advances in neural networks have enabled computers to better see and understand the world. They can recognize school buses and zebras and can tell the difference between Maltese terriers and Yorkshire terriers. We now know what it takes to train these neural networks well, but we don't know so much about how they're actually computing their final answers. We developed this interactive deep visualization toolbox to shine light into these black boxes, showing what happens inside of neural nets. In the top left corner, we show the input to the network, which can be a still image or video from a webcam. These black squares in the middle show the activations on a single layer of a network, in this case the popular deep neural network called AlexNet running in Caffe. By interacting with the network, we can see what some of the neurons are doing. For example, on this first layer, a unit in the center responds strongly to light to dark edges. Its neighbor, 1 neuron over, responds to edges in the opposite direction, dark to light. Using optimization, we can synthetically produce images that light up each neuron on this layer to see what each neuron is looking for. We can scroll through every layer in the network to see what it does, including convolution, pooling, and normalization layers. We can switch back and forth between showing the actual activations and showing images synthesized to produce high activation.
We'll go into this in a bit.
By the time we get to the 5th convolutional layer, the features being computed represent abstract concepts. For example, this neuron seems to respond to faces. We can further investigate this neuron by showing a few different types of information. First, we can artificially create optimized images using new regularization techniques that are described in our paper. These synthetic images show that this neuron fires in response to a face and shoulders. We can also plot the images from the training set that activate this neuron the most, as well as pixels from those images most responsible for the high activations, computed via the deconvolution technique. This feature responds to multiple faces in different locations, and by looking at the deconv, we can see that it would respond more strongly if we had even darker eyes and rosier lips. We can also confirm that it cares about the head and shoulders, but ignores the arms and torso. We can even see that it fires to some extent for cat faces. Using backprop or deconv, we can see that this unit depends most strongly on a couple units in the previous layer conv4, and on about a dozen or so in conv3. Now let's look at another neuron on this layer. So what's this unit doing? From the top 9 images, we might conclude that it fires for different types of clothing. But examining the synthetic images shows that it may be detecting not clothing per se, but wrinkles. In the live plot, we can see that it's activated by my shirt, and smoothing out half of my shirt causes that half of the activations to decrease. Finally, here's another interesting neuron. This one has learned to look for printed text in a variety of sizes, colors, and fonts. This is pretty cool, because we never asked the network to look for wrinkles or text or faces. The only labels we provided were at the very last layer, so the only reason the network learned features like text and faces in the middle was to support final decisions at that last layer. For example, the text detector may provide good evidence that a rectangle is in fact a book seen on edge, and detecting many books next to each other might be a good way of detecting a bookcase, which was one of the categories we trained the net to recognize. In this video, we've shown some of the features of the DeepViz toolbox and a few of the things we've learned by using it. You can download the toolbox at this URL and explore it for yourself. If you'd like to share what you find, you can use the hashtag DeepViz. Thanks for listening, and we look forward to seeing what you discover.
Yep. So that's DeepViz toolbox. Pretty cool. Did you guys hear it, by the way? Was it? Okay, awesome. So that's pretty cool, right? So you can investigate these and debug them in real time. So two kinds of visualizations, again, that he presented there are deconv-based approach and optimization-based approach. And we'll go into those now one by one. So I'll show you first how we generate some of the deconv images that he showed. So before we actually dive into it, I'd like to kind of start off with a question. Suppose I feed an image through a convolutional network and we get all these activations throughout. Think about how can you compute the gradient of any arbitrary neuron in the network with respect to the image. So in other words, the gradient on the image for any arbitrary neuron in the network is computable. Of course, it's a smooth function because the convnets are a differentiable function. But how would you actually compute that in a code base? Like say you're working on your assignment and you have your forward, backward, your layers. What is a practical, easy way to actually compute this gradient with respect to any arbitrary neuron? So normally what we're computing gradient with respect to is we have this entire computational graph where we pass the image through and we get a loss at the end. And then we, if you remember your computational graphs, we start out the backpropagation by setting a 1.00 gradient there because we want the gradient with respect to loss. The gradient of the loss with respect to loss is 1.0, and we run backprop backwards and find the influence of all the inputs on that output. So how would you do it now if you wanted a specific unit in the convnet and find gradient for it?
Backprop from there.
Backprop from there, okay. So we do a forward pass, and then suppose we're interested in some layer and that neuron. What would you do?
Stop there and backprop.
Just stop there and backprop. So you have to start off with like some gradient, right? So what we'll do is we forward until some layer, and then we have our activations at that layer, and now we're interested in some specific neuron. We'll zero out all the gradients in that layer, except for the neuron's gradient. We'll set that gradient to 1.00, and then we run backward from that point on. And then when you backprop to the image, you'll find the gradient of the image with respect to any arbitrary neuron by meddling with the gradients. And so in particular, we want to set the gradient of the one we're interested in to be 1.0. And so, yeah.
Why don't we just use like numerical gradient as a way to compute the gradient?
Why don't we just use the numerical gradient? Because it's just slower, right? So we could use a numerical gradient to also compute the gradient with respect to any arbitrary part of the network, but it's just you'd have to iterate over all the pixels one by one, and it would just be slow. So this way we can use the analytic gradient, right? We're just doing backpropagation and just computing it right away using calculus. So for example, if we wanted the gradient not with respect to the loss function, but in this computational graph we wanted the gradient for this guy here, this gate, then what I would do is I would run the inputs forward until this gate, and then I would stop right there, and I would just set 1.00 as the gradient at this point, and I would just run backpropagation from here. And whatever gradients I obtain here are the basically gradients, the influence of these neurons on this guy. So that's how you can compute your influence on any arbitrary part of the network. So when you do that with an image, you suppose we wanted to like pick on an arbitrary neuron. You take an image, you forward it through, and you do what I described. You set the gradients to all 0 except for a neuron you're interested in, and you run backward from there. And you'll find, for example, looking at an arbitrary neuron, you'll find something like this as the gradient on the image. So you can see that it's not very easily interpretable. It's kind of like these blobby things. It looks kind of strange. So deconv approach will change the backward pass a bit to actually give us nicer pictures. So in this case, for example, we'll use what's called guided backpropagation, and we'll actually obtain much cleaner images of, say, this cat's head specifically. So that neuron would be positively influenced by this cat's face specifically, and we'll see how we can get rid of these artifacts. And so the way this will work, this deconv approach works, is I'm going to go through a figure from the paper. This is Striving for Simplicity paper, so I have to explain this a bit. So here we have the input image goes through a series of layers, and we get some activation feature map at some point in the convnet. And now, as I mentioned, if we'd like to derive the gradient for any arbitrary neuron here, say like this neuron in the bottom right, we'd zero out, so these are the gradients now in this second row here. We'd zero out all the gradients except for that neuron, and we'd do backpropagation to find the reconstructed image, as they call it. But really, it's the backward pass here. Now, when we're doing backprop, it turns out that to get your deconv approach to give you nice interpretable pictures, we're going to be running backpropagation, just like in a previous slide, but we'll meddle with the backprop for specifically the ReLU layer. So the ReLU layer just thresholds things at 0. We'll change the backward pass for a ReLU layer, and otherwise we'll run backward through the image. And you'll see in a bit why that kind of makes sense. So we're looking specifically at a ReLU layer here and what it computes during the forward and backward pass during backpropagation. So if we're in some feature, this is some feature map in the COMNET, and we apply the ReLU operation, which is thresholding all the negative activations to 0. Now in the backward pass, this ReLU layer finds what the gradient from above is. So this is the gradient going into the ReLU neurons. And the way ReLU works, right, is it just kind of blocks all the gradient for all the parts that had negative activations, right? Because if you're a ReLU neuron, and there's a grid of 3 by 3 of them here, if you're a ReLU neuron, then if your input was less than 0, then you act as a switch during the backward pass, right? So if gradient comes from here, if you're a ReLU neuron and your input was less than 0, then you block the gradient, and if it was greater than 0, then you let the gradient pass through. So basically, that's what's going on in the backward pass here. So this is just backpropagation right now, and this is how you'd write it out. So basically, the backward pass for this ReLU neuron is the local gradient, which in this case is just a greater than 0 operation, and then times the gradient from above. So this is the chain rule going on here, how you backpropagate through ReLU. Now in guided backpropagation, what we'll do instead is we'll change the ReLU layer backward in the following way. We are computing what we had before, so ReLU pass, but in addition, we have this additional term here, which basically is saying that we only backpropagate through our ReLU neurons, only the activations, only the parts, the ReLU neurons that have positive gradient. So, okay, so this is the guided backprop. So normally we'd pass through any gradients that corresponded to ReLU neurons that received less than 0 input. And now for guided backprop, we're additionally going to block out all the gradients that that are negative gradients. So for example, some of these gradients that ended up passing through this ReLU layer in the backward pass were like -2 or -1 or -1 here. We're actually going to kill those. We only backprop the positive gradients. And so what's going on here is, think about the interpretation for what it means a positive or negative gradient in this case. We're trying to compute the influence on the input, from the input, on some arbitrary neuron in the COMNET. And what a negative gradient is saying is that this ReLU neuron has a negative influence on this neuron that we're trying to find what activates it highly. And this piece here has a positive influence, and these guys have negative influence, and so on. So what we're doing is, as we're recursing this modified ReLU neuron throughout the COMNET, which is made up of this conv ReLU blocks, we only end up passing through gradients that have a positive influence, entirely positive influence on the activations, without the negative influences. So normally what happens is through the COMNET, this gradient signal is flowing backwards through many ReLU layers, and there are all these paths of influence between the input to any of the output neurons that we're trying to compute. And some of the paths are negative paths, and some of them are like positive influences. And this gradient signal is really just neurons communicating to each other what should increase or decrease. And they're kind of fighting each other and adding up and so on. And so what ends up happening with backpropagation is, the reason you get weird looking things is that you have all these passive influence, some of them positive and some of them negative, from every single pixel to the neuron we're trying to see what activates it, and they kind of end up canceling out in a weird interference pattern. And so what we're doing in guided backprop is we're only keeping the positive influences and only backpropagating those through, and then you end up with much cleaner images. So what this is saying is that this pixel, there's a chain through the COMNET of positive, purely positive influences, and there's a very direct kind of entirely increasing chain of influences through the COMNET on the neuron that you're trying to compute. Intuitively. Go ahead, questions.
If the convolution kernel has negative entries, then it's not true. Right?
Sorry?
If the convolution kernel has negative entries, then if we have negative gradient, it might be turned into...
Yeah, so when you think about a COMNET, it's a stack of conv ReLU, and so on, to a first order approximation. Here we're only changing the ReLU activations. So in between every ReLU backward, there will be a convolutional layer backward. And that contains some positive and negative weights, and so you end up with some positive and negative gradients on the next ReLU layer. But then we, again, truncate, we throw off all the negative influences again. And so we keep doing this recursively through. Go ahead.
If you did the opposite and only kept the negative gradients, would you get a map of the strongest inhibitory features?
Yeah, so the question is, if we only kept the negative gradients instead, do we get a map of negative inhibitory features? I guess so, yes. I've never tried that. It's a good question. Okay. Oh, was there a question?
You're basically just applying ReLU backwards.
Yes, so we're doing backprop, just like everything is normal, just normal backprop, but you have to hack the ReLU backward pass. And in that ReLU backward pass, you don't just do what normally a ReLU neuron wants to do according to backprop, but you make sure that you only backpropagate to positive gradients through ReLU.
So could you use different activation function? Like instead of just taking positive, taking only very large positive or reasonably large positive values?
I see. Like if this was not just a ReLU, but say arbitrary neuron, I think, yeah, we'd have the same kind of effect. If it was 10H or something like that, you'd do the same thing. And so what ends up happening when you do this is you just get a much cleaner, you don't have all these positive negative paths like fighting each other in a way, and you only end up with kind of like these positive influences through the network that ends up getting painted. And so these are the kinds of visualizations you can get for different neurons. Every row here is a neuron, and this ends up, this is I think COMP6 and COMP9 respectively. And these are kind of, we forwarded some image through, we found that this neuron activates, and then we did this backward pass, but this hacked up backward pass using the hacked up ReLU neuron. And these are the kinds of visualizations you obtain. And so they're kind of this, you can see that some neurons are basically, and this is also showing the raw images cropped to the part of the image that this neuron is a function of, right? Because these neurons are arranged spatially, and their area of influence is different in the spatial image. So these are little crops from images which come from the part of the image that activates this neuron. So you can see that some neurons, these are the raw patches that activate them, that activated them strongly, and this is the kind of deconv pass from here. Now there's another way to do it, not just this approach proposed in this paper, but there's also something called a deconvnet. This is from a paper from Matthew Zeiler in 2013, and it hacks up in the ReLU backward pass as well, but in kind of a more funny way. It ignores the ReLU gradient, and it's just passing through the positive gradients without, it doesn't care if the activation is coming into the ReLU are positive or negative, it discards that term. And so you can see that backprop, a deconv, and a guided backprop is kind of both of them at the same time. So it's kind of funky stuff going on. But for deconvnet, that turns out to actually also work well. And then you get also pictures that actually seem to make sense. So in these cases, it's a similar kind of idea to the guided backpropagation, but we're not taking into account just like subset of neurons based on what happens to activate in the forward pass. So I don't know if I have very good explanation beyond this point, but basically it produces much cleaner pictures because we're only passing through the positive influences, entirely positive influences through the backward chain. So these are some visualization for the first layer, for the second layer. So we can see that some neurons here activate for different kinds of textures. If we go deeper into the network, we start to see that on the third layer, we get neurons that respond to some kind of like honeycomb shapes or cars, or yeah, lots of interesting pieces here. And as you go to the fourth layer, we start to get some object-like things. So say dog faces here, and so on. And so we're building up these features one at a time. So every conv is kind of combining these little pieces into a higher layer of abstraction kind of shape that grows over time. Go ahead.
Why are we considering the gradient, and what's the intuition behind looking at the gradient?
Yeah, so what this is telling you, the gradient really is telling you, like the reason that we see, say, red here in this person here, like that gradient is telling you that if you were to make this person's face redder, there would be more red in it, then that would have a locally positive influence on this neuron's activation. So basically, making a small step in the image in this direction would have positively influenced that neuron downstream, right? That's what the backward pass is telling you. It's telling you, that's what backpropagation is doing, is it's computing the influence, the gradient of every single input to whatever you're interested in, right? So, but in backward pass, you have all these positive, negative influences, and here we're cropping always the negative influences. So you end up with like a subset of the backprop pass, almost. You can look at it that way. Okay, so I'm not a huge fan of the deconv visualizations. We're going to go into the optimization-based visualizations, which I think make much more sense and are much more intuitive in terms of what's going on. So let me get into those. What's nice about the deconv approach is that you do a single forward pass, single backward pass, and you're done. You just visualize that hacked up gradient, and you get some visualization that looks pretty. In the optimization approach, we're going to have to do a bit more work computationally, but it makes a little more sense, I think. So what we're going to do here is we have a COMNet. And of course, everything is fully differentiable here. And what we're going to do now is we're going to try to optimize the image so that so the parameters of our optimization now will be image, and we'll be keeping the entire COMNET fixed. Normally, we optimize over the parameters in COMNET. Now we'll hold everything fixed. And we're going to be trying to maximize an arbitrary score in the COMNET. So optimization problem-wise, basically, we're trying to find an image I such that your score is maximized, and there's some regularization on I. So say L2 regularization, which doesn't, discourages kind of these pathological cases where some of the pieces of your input might be way too large or something like that. So it's regularization, and we're trying to maximize the score. And so the way this will work is we'll start off with, say, like a 0 image. We'll feed it into a COMNET and get some scores out. And now in terms of the gradient, again, as before, we're interested in some class score. So we set the gradient at that point to be all zeros except for a 1 at the score that we're interested in. And then we're going to do backward pass to find what change to make to the 0 image. So this is normal backpropagation now. We're not doing any more guided or anything weird with ReLUs. This is just straight up backprop. So forward. And now we are interested in some particular gradient signal because we want to increase some score. We do backward and we do updates. So we're going to iterate this over and over, and we're going to basically run optimization over the image to maximize a class score, subject to also a regularization penalty. Okay? So when you do this, the kinds of results you get, and we're doing updates on this image, so we're doing image updates instead of the weight updates, you get images like this. So here we are maximizing any class here, and this is the image that maximally activates that class's score. So we have dumbbells and cups and Dalmatians. You can see all the little structured patterns there. It's kind of fun to look at. Bell pepper, lemon, husky. Here we have, and also notice, for example, here's goose. You can see that the optimization is really trying to take advantage of all the area it possibly has to increase the score of goose. So it like tiles the entire input with goose everywhere because it's just like trying to blow up the score of goose. So 1 goose is good, but 10 gooses is much more likely goose. So that's why that happens. Another kind of interesting way of interpreting the gradient signal at the image, and one way you can use it in an interesting way in this paper from Kieran Simonian is as follows. They have these fun experiments where they take an image, like say this dog, and they forward the image through the COMNET, and then it says that this is some kind of a special terrier or something. And then you set the gradient for that terrier to be 1, and you do backprop. And you arrive at your image gradient. And then what they do, this is kind of a confusing notation here, but they squish it through channels with a max. So basically, they're trying to compute a heat map here, a one-dimensional kind of map of these gradients. And so what might you expect, or what would you hope, or maybe happens in terms of what this might look like? We're visualizing these gradients.
High on the object location.
Okay, so you'd expect that it's high on the object location? I guess that's reasonable, right? So basically, this is what happens. So you end up with something roughly like that, where the gradients, the max of the gradients, without taking into account its sign, are these blobby things. And so really, the way to interpret these maps is its strength of influence of every single pixel on the score. So the fact that some of this stuff is black, what that's telling you is that if you wiggle that pixel, the score of that dog is basically not modified at all. So the COMNET doesn't care about it. But if you start to meddle with the pixels on the dog, then it's going to actually influence the score in some way of the dog. And so this is kind of telling you area of influence in the image. That gradient signal can be kind of used as a measure of area of influence of every single pixel on the score. Go ahead.
So with the slide before, you start at zeros and you arrive at some optimal image. I was just curious, how sensitive is that to choice of image? Like if you instead started with random image and optimize that?
Yep. So you're asking how sensitive are these optimizations to the initialization? We'll see actual examples of that in like 2 slides. Yeah?
And also with the previous one, rather than having like that ridge regression term on there, why don't we just like put a hard max at like 255 or something like that?
Yep.
Which would be a little bit more of a...
Yeah, so you're asking about the precise forms of regularization used here and the fact that you could use multiple. There's in fact a paper we'll go into in 5 slides where they actually talk about this regularizer quite a bit more, and you want to choose it properly, and there are multiple choices here. So what's interesting here is they have these experiments in the paper where you can actually use that gradient and you can use a grab-cut segmentation algorithm, which we won't go into, but that is the input to grab-cut, and basically grab-cut does this joint optimization over pixels and you basically want similar pixels or nearby pixels to have the same label. And you can actually crop out some of these images just based on the gradient signal on the raw image. And so I should like to say that these are kind of, I suspect, cherry-picked examples in this paper, because I think we tried it in some of our stuff, and you don't always get this nice looking things. But in principle, you can imagine that this might work sometimes. Okay. So right now we were maximizing, I was showing you examples of maximizing the full score, and we were doing optimization of the image. And the point here is that you can actually do this for arbitrary neuron in the COMNet. We saw this with DCOMP as well. And so the way this would work is, again, we have an optimization over not just the score, but maybe any arbitrary activation of any neuron in the network. And there's this penalty L2 that we've been using so far. In this paper from Jason Yosinski, they argued that actually there are better ways of regularizing, and they were looking for different ways of regularizing the image to make it more image-like. And they actually found a different kind of more explicit scheme that they found worked better, and we'll see another set of visualizations that make everything look a bit better, I think. And the way they do it is they ignore this penalty. Instead, they just maximize a neuron, but after they do forward and backward, they do an update, and then they blur the image a bit. So if your image here is X, they do forward, backward, they do a small update on the image, and then they blur it. And so this blurring that you keep doing at every single iteration, it's kind of like preventing the image of accumulating high frequencies. Not through the loss function that you're optimizing here, although I think you can re-express it as the blur kernel here corresponding to some total variation loss function. But they do it more explicitly like just a blur. And then they do a bit more sparsely encouraging things that I don't want to go into. You can check the details in the paper. But basically end up with cleaner visualizations for classes, I think. So here are some flamingos or pelicans or hartebeest. So these are classes at the very end of the COMNet, and we're optimizing these images to maximize that class. So these images are in fact equivalent to the image that I've shown you before. The experiment is doing the exact same thing as here, but it's using a different regularizer. And so you see that instead of the L2 norm, this one I think looks a bit better. To your question in terms of how much does initialization matter, they are showing 4 different crops here, 4 different results for different initializations. So you can get a sense of like there is some influence of initialization. Okay, so this is at the last layer of scores, but we can actually go down the COMNet and repeat the optimization process for arbitrary neurons. So on layer 7 and 8, things are not as clear yet, but once you descend down the COMNet, you start to get really interesting visualizations. So on layer 6, it's still kind of a bit of a mess, but I think on layer 5 is where we start to get some very interesting, like neat looking things. So this is some little pieces of ocean perhaps, or this is some kind of spider looking thing or text looking thing, right? So you can see that these are the images that maximally activate these neurons. They're actually quite interpretable in some cases. On the layer below, we have these pearl looking things or squiggly looking things. And so these just come out of the optimization. So this kind of gives us some idea of what these neurons really like to see and what they're firing for, what they're looking for in the image. Go ahead.
Does the granularity of the feature depend on the total number of layers? Like would layer 7 be more abstract if you had 200 layers?
Yeah, so the question is, would the layer 7 be more abstract if you had 200 instead of just like 7 layers? A very difficult question. Actually, yeah, it's not clear to me.
So one thing that does tend to matter when you do these visualizations is the effective receptive field of different kernels. So if you think about like which parts of the input image could possibly affect different neurons, as you go deeper, there's sort of larger space in the input that actually even has a chance to affect that thing. So that's part of the reason why you tend to get bigger, nicer looking things as you go deeper in the network and visualize these things.
Yeah, so think about what we call the effective receptive field of every single neuron along the network. In the first layer, the effective receptive field, say for a VGG net, is like 3 by 3, right? But then as you go deeper in the network, you find that these neurons are a function of larger and larger areas in the original image. And so that's why you see for this layer 4, you see more localized, smaller pieces of image. And for a higher up, you see kind of more blobby things. So my guess would be if you have 200 layers, by layer maybe 20, maybe like 7 or 8 or 9, you'd have to do the math. But by that layer, you're probably seeing neurons that are a function of the entire image. And so you'd get just these kinds of things, I assume. And then for layer 3 to 1, we have again, yeah, it's self-explanatory. Looks fun.
So that's